So good morning to all. So we are going to see our third unit, robot mechanics. Okay. So in the case of robot mechanics, so we know that we are in need to see about robot kinematics and what about the introduction for the matrix representation and what about the rigid motion, homogeneous transformation, and then forward and the inverse kinematics and what about the trajectory planning? Okay, so we can divide the robot mechanisms into two parts: robot kinematics and robot dynamics. Okay, so that we'll be having about the introduction, manipulator dynamics, what about the Landry unit formulations and Newton unit formulations. Okay, so when we all know that the robot actually it is a machine capable of physical motions for interacting with the environment. Okay, and when we are saying about the types of robot mechanisms, so we know that we'll have a pneumatic, hydraulic, as well as we have a electric also. Okay, so in the sense, uh, so we actually the robot mechanics on the part of Dina, it will cover the mechanical engineering aspects of robot design. At the same time, it includes the factors such as inertia, stress, load varying capability, and dynamic response. Okay, and then so here this mechanical engineering will also be involved in the design of grippers, transmission systems, hydraulics, and pneumatic couplings, as well as related design areas overall. Okay, uh, so the main concept which is involved in the robot mechanics are to be the study of the kinematics, what about dynamics, what about motion planning, what about the control of mobile robots and the robot arms. Okay, so the first thing actually we are interested in two kinematics topics. Okay, so the first thing will be about the forward kinematics and inverse kinematics. Okay, so robot kinematics, when we are saying about this, it applies geometry to the study of the moment of multi-degree of freedom that change that forms the structure of robotic system. At the same time, uh, the emphasis on the geometry, which means that the links of the robots are modeled as rigid bodies and its joints. They have been assumed to provide few rotations of translations. Okay, so kinematics அப்படின்னாலே என்ன அப்படின்னு பார்த்தோம் அப்படின்னா it is the study of the relationship between robot joint coordinates and the spatial layer. Okay, and when we are saying about types of robot kinematics, actually apart from forward and reverse, so we'll have a broad classes only to be the serial manipulator and other one to be the parallel manipulator. Okay, and forward kinematics வந்து பார்த்தோம் அப்படின்னா we'll be calculating from angle to position, whereas inverse kinematics வந்து will be calculated from position to angle. Okay, that is what it will be given அப்படின்னா the length and the angle of each joint will be given. We have to find out the position of the coordinates x, y, and z. Similarly, in the case of an inverse coordinates, will be given about the length and the position, the angles of each joint needed, so that has to be find out over on it. Okay. So robot kinematics. So I have shown over the diagram over here. So we'll have a joint trajectory motion. So when it is moved from over here, that is the you will compute end effector motion in terms of given joint motion. That is to be the forward kinematics. Whereas inverse kinematics வந்து பார்த்தோம் அப்படின்னா it will compute joint motion in terms of given end effector motion. Okay, so the computing end effector, computing joint motion. So this is the difference between the forward kinematics and inverse kinematics. The next thing we have to study about the robot dynamics. So whereas robot dynamics, it says about it. So whereas in the case of an robot dynamics, actually it is concerned with the relationship between the forces. Okay, it is concerned with the relationship between the forces acting on the robot mechanism and the accelerations what they have produced. So it will be depending on the robot mechanism and accelerations what they have produced. Okay, so robot mechanism அப்படின்னு எடுத்தோம் அப்படின்னா it is modeled as a rigid body system. Okay, that is the robot dynamics. This is the applications of a rigid body overall. Okay. And when you are saying about again we have two different classifications, one to be the forward dynamics, another to be the inverse dynamics. So in the case of forward dynamics, it will be computing end effector motion in terms of control tasks. Similarly, whereas inverse dynamics will be computing joint control forces in terms of end effector motion. Robot controls, so these are to be the controls which is second over on it. So we'll be giving the task command. Task command will be given to the controller, where we have a joint command. end effector task set it. So we'll have a sensor. So in order to get a feedback, so based upon the feedback, the operators will be giving the task command. So in order to attain the desired end effect task, so we'll have a robot controls overall. Okay. So next thing we have to do the matrix representation. So matrix representation. So we have to consider the representation of a point in space. So a point P in space will have a three coordinates x, y, and z. So we'll have a relative frame. So relative frame which is to be given in terms of an P is equivalent to ax I vector plus by j vector plus ez k vector. So this is a normal representation of a point in a space. So if you are defining vector notations பண்ணும்போது நம்ம என்ன பண்ணுவோம் நம்ம உங்களுக்கு so we'll have the vector notations x, y, z and w, where w represents for the scale factors. This will have a three coordinates of its plane and of its x. Okay. So this is about the representation of a vector in space. This is the representation of a point in space overall. Okay. So next thing, scale factor. Scale factor, we have to define what is scale factor W. So that is, it can change overall size of vector, similar to zooming function in computer graphics. It can change overall size of vector, similar to zooming function in computer graphics. That is when W is equivalent to 1. So it depends on the factors. It can be either of 1 or a 0. When W is equivalent to 1, what will happen? Size of components will remain unchanged. Similarly, when W is equal to 0, it represents a vector whose length is infinite, but it represents the direction, so it's called as a directional vector. The next thing we have to do about the matrix representation. So in the representations on the path of so the representation of a frame at the origin, which is to be fixed over here, it is to be named as a reference frame. Okay. So each unit vector on the path of will be mutually perpendicular. So we'll have a normal orientations and approach vector. So we'll have a origin of the reference frame over there. And next, so we'll have a x, y, z with the values of a, o, and n. So all these factors n with respect to x, with respect to y, and z, similarly o with respect to x, y, and z, and a with respect to x, y, and z overall. Okay. And the representations of a frame in a fixed reference frame. So each unit vector is usually perpendicular. We have a normal orientations and the approach vector. So we have to consider the point P in the space over on it. So we'll be considering Px, Py, Pz. So with the unit matrix of one vector over on it. So similarly, the next thing we have to represent the rigid body. So முதல்ல வந்து நம்ம point P space எடுத்துட்டோம். Fixed frame எடுத்துட்டோம். Next வந்து rigid body எடுத்துட்டோம். So rigid body ல வந்து நம்ம எடுத்துட்டோம் அப்படிங்கும்போது the same thing that we'll be representing over on it. So this is for an object. So object வந்து which can be represented in space by attaching a frame to it and representing the frame in space over on it. So we have to do the homogeneous transformation matrix. So a transformation matrix it must be in a square form. So it is much easier to calculate the inverse of square matrix. So in order to multiply the two matrices, the dimension must match over on it. So when you are seeing over here, the dimensions over to be the 4 cross 4 and this also be 4 cross 4. So when you are multiplying both this thing, we'll get able to get the factors. So the factors what of an f is equal to nx, ox, ax, px, ny, oy, ay, py, and nz, yz, az, pz, and 000, 1 will be there. Okay. The next one thing we have to see about an transformation. So transformation, which is defined as making a movement in space, which is defined as movement in a space over on it. Okay. So in this space, so what are all the transformations which are available over on it? We'll have a few translations, few rotations, and then combination of translation and rotation. Okay. So here we'll be using the translations and rotations. They are to be named as an alternating terms, which is for position and orientation. Okay. That is the robotic systems, which commonly used in robotics, which allow us to convert between them. So when we are defining a transformation matrix, by multiplying the translation matrix with the help of an rotation matrix. So we'll be using terms to be as a homogeneous transformation in robotics. It is which is a tool describing for both the position and orientation of an object, and in particular of a robot or robot component. Next one, representation of few translation. So how we'll be having about a representations of a few translation. Okay, so few translation. So that is if a frame moves in a space without any change its orientation. So for example, when we are saying a translation it is a displacement in which no point in the rigid body will remain in its initial position. lines in the rigid body வந்து பார்த்தோம் அப்படின்னா will remain parallel to their initial orientation. Okay. So translations அப்படிங்கிறது என்ன சொல்றோம்? It is a displacement in which no point in the rigid body remain in its initial position. At the same time, and all straight lines in the rigid body remain parallel to the initial orientation. Okay. So we'll have a frame move over here. So we'll have a point with respect to A, O, N, and we'll have the next thing D. So D matters with respect to A, O, N. So we have to write down the matrix with respect to A,